Hello, let's continue working on some equilibrium problems. So this one says that the K for the reaction between hydrogen and iodine to form hydrogen iodide is 55.17. It says if you place 1 mole of each of hydrogen and iodine in a half-liter flask at 699 Kelvin, what are the equilibrium concentrations of all your species, the H2, I2, and the HI? So since it's an equilibrium problem, we're going to start with the K EQ expression. So KEQ is equal to the concentration of HI squared divided by the concentration of H2 times the concentration of I2. We are given that the equilibrium constant, the KEQ, is 55.17, and we're trying to find all the other concentrations. So in this case, since we don't know any of the concentrations at equilibrium, we are given some form of concentration here. It's 1 mole of the hydrogen and the iodine in half a liter, but that's initially. That's not at equilibrium, and so that means we need to make an ice chart. So let's do that. So I have H2 plus I2 yields 2HI, and ice, so initial. So for the initial concentration, it tells us that we have 1 mole divided by 0.5 liters. So let's see. Concentration initially of the H2, 1 mole divided by 0.5 liters. So that's going to be 2.0 molar. And that's the same for the I2 initially as well. So for the ice chart, initially this is 2 molar. And this is also 2.0 molar. And initially we don't have any product yet, so that's 0 molar. Some of the H2 is going to get used up, and some of the I2 is going to get used up. So let's say that the amount that they get used up is X, and so we're going to remove an X amount from H2, and it's going to be the same amount from I2 because it's a 1-to-1 ratio. For the products, we're going to form 2X because it's a 1-to-2 ratio, so plus 2X. So then at equilibrium, this is 2 minus X, 2 minus X, and then this is 2X. So let's plug these in back into our equilibrium expression. So our KQ is 55.17. Our HI concentration is 2X. So that's 2X all squared. So that's really 4X squared. Divided by 2 minus X times 2 minus X. I'm going to give you a minute to go ahead and plug it into your calculator to solve for X here. And if you're still struggling figuring out how to get those values from your calculator, make sure that you get some help from one of your friends or from your math teacher. If you are somebody who is pretty good at this and figuring out different ways to do it, or really good with the window and adjusting it, please help others. A lot of people struggle with using their calculator to find X here. Okay, so hopefully you plugged it in. I got that X is equal to 1.58, and this is a concentration, so molarity, molar. And so my question was asking for the equilibrium concentration for all species. So concentration for HI at equilibrium is 2x. So 2 times 1.58 is 3.16 molar. Concentration of H2 is the same as the concentration of I2 at equilibrium. They are both right here, 2 minus x. So 2 minus 1.58 molar. And so that gives you 0.42 molar. So that's a 4 there. All right, let's move on to the next one. So the next one says, in the previous question, so we're still talking about H2 and I2 forming HI. Suppose that the initial concentration of H2 is 1 molar and the initial concentration of I2 is 3 molar. So they are different concentrations. What are the equilibrium concentrations of, again, all species? So it's exactly the same question as the previous one, except right here your initial concentrations are different. One of them is 3 molar and the other one is 1 molar, as opposed to both of them being 2 molar. So we're going to do the same exact thing, just with a different ice chart. So here, my ice chart, let's see, we have H2 plus I2 yields 2HI. Alright, ice. So the initial concentration for the H2, they tell us, is 1.0 molar this time. The initial concentration for I2 is 3.0 molar. And again, the HI is a product, it has not formed yet, so initially it's 0 molar. The change in this case is still the same. We're going to use a certain amount of H2, we'll call it X. Because this is a 1-to-1 ratio, we're going to use the same amount of I2 to react with the H2, so minus X, and we're going to form 2X in terms of HI because it's a 2-to-1 ratio still. The equilibrium, this is going to be 1 minus X, this is going to be 3 minus X, and this is going to be 2X. So then our KQ expression, 55.17, is equal to the HI concentration, so 2x squared, divided by the H2 concentration is 1 minus x, times the I2 concentration is 3 minus x this time. And again, I'll give you a minute to plug it into your calculator and solve for x. And please help each other figuring this out on the calculator. A lot of times if you're having trouble, if it gives you an error, that means your window is not adjusted. So what I do is I don't adjust my window, I just try it first, and then if it gives me an error, then I go back and look at my window and see if I can figure it out. For this one, when I plugged it in, I got that X is equal to 0.97 molar. Okay, so now to figure out all your concentrations, let's start with H2. So H2 at equilibrium is equal to 1 minus X, so 1 minus 0.97, and so that's 0.03 molar. For I2, that's 3 minus X, so 3 minus 0.97, so that's 2.03 molar. And then the concentration of HI at equilibrium is 2x, so 2 times 0.97, and so that's equal to 1.9 molar. Let's try the next problem. It says I have 100 milliliters of 0.02 molar lead nitrate. It's mixed with 150 milliliters of 10th molar sodium chloride. And it's asking, will a precipitate form? And they give us the KSP for PbCl2. So let's look at what's happening here. So I have two solutions. So I have 100 mils of 0.02 molar of the lead nitrate, and I have another solution that's 150 mils of 10th molar NaCl, and I'm going to mix them together. Now, if I mix those two together, lead nitrate and NaCl, if a precipitate forms, what precipitate would that be? So if I mix those two together, one of the products would be NaNO3, sodium nitrate. That's very soluble. That would never precipitate according to the solubility rules. Remember, you need to know that one rule. The other one is PbCl2, which actually is slightly soluble, or, in other words, insoluble. Now, if you didn't know that, they kind of told you the KSP for PbCl2 is 1.4 times 10 to the negative 8, so that's a pretty small number. Remember, K, whether it's KQ or KSP or KC, those Ks, the equilibrium constants, tell you whether a reaction is product favored or reactant favored. So this is a very, very small number. This is 0.000000014. So it's a very small number that tells you it's very reactant favored. So that means not very many of these are going to dissociate or dissolve. And so that tells you this would be the precipitate if there was a precipitate to form. So the KSP is for salt, an ionic salt, dissociating. So let's write down that process. So PbCl2 solid dissociates into Pb2 plus ions and 2Cl minus ions. The KSP, the expression for this, would be the concentration of Pb2 plus times the concentration of the Cl minus. Don't forget to square it. And then you do not include this. You don't divide by this because that's a solid. You don't include it. You only include the aqueous ions or if you have gases. So that's my expression. And they tell us that that number is 1.4 times 10 to the negative 8th. Okay, so then how does this help me? So when I mix these two together, I can figure out what the concentration of Pb2 plus is and the concentration of Cl minus is, and I can calculate the concentration right now, which would be Q. And I can compare that to this number, so I can compare Q to K, because this is when it's going to start precipitating. So I can compare Q, which is my reaction quotient, this expression right now, versus when it's at equilibrium, and find out if I'm at equilibrium, so it's going to start precipitating, or if I'm before that, or if I'm after that and it's already precipitated. So let's do that together. So we're going to find Q. So Q is the concentration of Pb2 plus times, that's a 2 plus there, times the concentration of the Cl minus squared. Now what is the difference between this expression and this expression? Because they look pretty similar, right? This is right now. This is specifically at equilibrium. So for Q, I can plug in my concentrations right now, whatever they are when they're mixed. This only applies when we're at equilibrium, and we're talking about equilibrium for a solution. That means when it's fully saturated. So any extra, it's going to precipitate. It's about to precipitate when you're at equilibrium. That's what equilibrium means for making a solution. So right now, I'm going to plug in the values for the Pb2 plus and the Cl minus concentrations. Now, it's not these concentrations. Why not? Because when I mix them, the volume changes. And so I have to figure out, when you mix these two solutions together, what is the concentration of the Cl minus and what is the concentration of the Pb2 plus. So let me do that on the side. So let's start with the Pb2 plus. So the Pb2 plus concentration, I have 100 mils, so 0.100 liters, and it's 0.02 molar, so 0.02 moles per liter. That gives me the moles of Pb2 plus, and then I divide by the total volume. The total volume is 100 mils and 150 mils, so that's 250 mils, which is 0.25 liters. So the concentration of the Pb2 plus when you mix the two solutions is 0.008 molar. Let's do the Cl minus in the same way. So I have 150 mils, so that's 0.15 liters. It's 10th molar, so 0.10 moles per liter. Multiply those together, you get moles, and then divide by the total volume, 0.25 liters. And so the concentration of the Cl minus is 0.060 molar Cl minus. So these are the concentrations of the Cl minus and the Pb2 plus when you mix the two solutions together. So I'm going to plug these in into my Q expression. So 0.008 molar times 0.060 molar squared. So Q ends up being 2.88. I'm not really looking at sig figs here, because we're just trying to figure out if a precipitate forms or not. Times 10 to the negative fifth. And that's my Q. So now what does that mean? Well, if when you multiply these two together, the Pb2 plus times the Cl minus squared, if you get this value, then you're at equilibrium. So that's when it starts precipitating. So what you do is you compare Q to this value. You compare Q with KSP. So in this case, is Q equal to, greater than, or less than KSP? So in this case, it's much larger than the KSP. Remember that KSP is products over reactants. And so right now my Q is way larger, right? What does that mean? That means my products are way larger than they would be at equilibrium. And so that means that a precipitate will form. If your Q is lower than your KSP, that means these concentrations of my ions is very, very little. Not very much has dissolved. So very little of this is there, and so it's not going to form your solid. If Q is much larger, that means I have way too much of these than I could at a saturated solution, so that means the extra will precipitate. So in this case, a precipitate will form.